Looking at the example that we've got here, which is set 15, question 12. A cycling velodrome track is so banked at a certain point where the horizontal radius of curvature is 30 metres, and the cyclist may make the bend at 16 metres per second, so he's going into the board. At that, without depending on the sideways friction force of the tyres, what is the angle between the horizontal and the track? So if that's going to be the case in that regard, what forces are we looking on the cyclist? Well, he's going to have weight force pulling him down. There's going to be a normal force acting at right angles to the track. Now, if that's the case, then let us have a look at this normal forces acting at right angles to the track and find the components, the horizontal component and the vertical component. So this one will be force in vertical, force in horizontal. Now we can show, okay, that this angle here is going to be this angle here. Okay? Because we know that normal, we know that that angle in there is 90 degrees. We also know that the angle between Fn and the horizontal is 90 degrees. So basically what that means is this angle here is 90 minus theta. And if that's the case, then that straight line through there, if that's 90, then that's 90 minus theta, and you add that up to 180, then that angle in there has to be equal to theta. Gives you a bit of basic geometry. So what that gives us, and I'll draw it over here so it's a bit clearer, is that we have the normal force coming off the track, then we've got the force normal horizontal, and then the force normal vertical, and that angle there. Now, at that point, the force normal vertical and the force due to gravity are actually the same. They are opposite, and it's not accelerating up or down. So that one there is going to be equal to mg. Now, the component of the force of the normal that is coming this way is going to be the force that's pulling it out this way. So what we have there is that is going to be the centripetal acceleration force, or centripetal force. Which equals mv squared 1r. Now, looking at your so if that's going to be the case, then what we have is force of normal horizontal is going to be equal to, using our basic trigonometry, that one is equal to the force of normal cos of theta. In this case, theta, cos of theta is equal to the vertical one. Should we look at that one? The vertical one is equal to, the cos of that one is equal to the adjacent over the hypotenuse. So if we rearrange that, we get that. We also have force normal horizontal similarly. That's going to be equal to mg. This one's going to be equal to f in sine theta, which is going to be equal to m V squared on R. Now if you rearrange the equations we get, if you rearrange that one, f of n equals mg on cos theta, just using that section there. We put that into the second equation, and what we get, mg sine theta, we replace that one, mg sine theta equals mv squared on r. And the beauty about this one is that it's independent of mass. The masses cancel out on both sides, and then we get sine theta equals v squared on g r. Oh, hang on. Got it too. I've missed out across there. So, therefore, mg sine theta cos theta equals mv squared on r. And if that's the case, well, we know that sine theta on cos theta is the same as opposite on hypotenuse all over adjacent on hypotenuse, which equals opposite on hypotenuse multiplied by hypotenuse on adjacent. They cancel out, equals opposite over adjacent. And what does opposite over adjacent equal? Tan theta. So that is equal to tan theta. So mg tan theta equals mv squared on r. Now we can cancel out the m's. We get tan theta equals v squared on r. Therefore, if you want to find out what theta is, you're going to have tan minus 1 v squared on r. So that should be a g in there as well. G tan theta, so bring that across. So in order to find this out, tan to the minus 1, v squared, what did we say that was, 16? On 9.81 times 30. If you work that one out, you'll be able to find out what the angle is. So there's a relationship between the car's velocity and the radius of curvature and the angle of the bank that is independent of the car's mass. This equation represents the ideal scenario where all of the centripetal force is due to the normal force and none is provided by friction. In practice, a car could go faster than this up to the limit of the frictional force provided by the road. And then it will just go flip off. Okay. Are there any questions on that?